Welcome everyone to the Lawrence Berkeley Lab Retirees Association quarterly seminar. And we have today with us Jonathan Carter, who's the ALD, Associate Lab Director for Computing at the lab. And he has taken some time out of his very hectic schedule, compounded by all that's going on today, to give us a peek at how the lab is developing, utilizing this technology for furthering research. And let me turn this over to Lynn to formally introduce Jonathan, and we can go from there.
Okay, excuse me. For the record, this introduction was not prepared by ChatGPT. It was done the old-fashioned way, old school plagiarism. So our speaker, Jonathan, is Howard mentioned. Well, he holds a PhD in theoretical chemistry from the University of Sheffield in the United Kingdom. And he is, as Howard said, the lab's ALD for computing sciences. In his ALD capacity, he oversees the Computational Research Division, NERSC, and ESNet. At the lab, he's played a key role in procuring, deploying two of the world's fastest supercomputers at NERSC and helped lead several initiatives within the DOE National Lab System, most notably the Exascale Computing Project and the Quantum Information Science Initiative. Before coming to the lab, he was a staff scientist at IBM's Almaden Research Center. He was one of the lead authors of the DOE report, AI for Science, Energy, and Security, which well positions him to discuss artificial intelligence and how it is poised to advance discoveries in materials, energy, chemistry, physics, biology, and probably as many other scientific fields as we can imagine. So welcome, please, Jonathan Carter.
Thanks very much for that introduction, Lynn and Howard. And some of you may be wondering why a chemist is running the computing organization. And I guess my response is, well, Angela Merkel and Margaret Thatcher were also chemists. So chemists get around and do different things. For today, I liberally borrowed from my colleagues at the lab, because I wanted a number of different stories of how AI is being used. I'm not a fundamental AI developer, but I use many of the products and help improve them for the kinds of things that I'm interested in. So I'll kick off. Actually, Robert, you have your hand up.
Hold on one second. I have to. Okay, Bob, you can ask your question.
My mistake, sorry.
Okay.
Just very briefly, then, tend to use some of these words interchangeably, but I think of AI as kind of the biggest object, as it were. Basically, any way we could program a computer to enable it to respond to situations, much as any other intelligent being could. And then machine learning, I think of that as a subset of the big problem of AI. And machine learning, what you tend to do is you tend to have some data, either a lot or perhaps not so much, and you use statistical techniques to enable the machine to learn something from that data so it can take some decisions maybe in the future. And then what has become really very popular, for instance, ChatGPT is kind of a form of this, is deep learning, which is, again, a subset of machine learning. And that specifically uses artificial neural networks with multiple layers to learn from the data. So there's many ways you could think of learning from data, but deep learning is just one way that you can do it. And deep learning is kind of brain inspired. So, I'm not a neuroscientist, and I think many neuroscientists think that's not the physical architecture of the brain, but that's how most of these artificial intelligence methods are currently constructed, by having these networks of basically artificial neurons that need to be trained. And then you probably hear other variants of machine learning, and let me just go through them quickly, because I might use this vocabulary in some of the examples, and I want you to have an idea of what I'm talking about. So probably the easiest is what they call supervised learning, and so you can imagine that you imagine that you're you're searching for pictures of kittens playing on YouTube, say. And so YouTube has to figure out a way to label all the videos with kittens on. And they're not going to have a person do that. They're going to have a machine do that. So the training set is they have lots of pictures of kittens that are labeled, this is a kitten. And so the machine ingests those. It has some kind of internal representation of what it thinks a kitten is, and then it uses that data to classify other images that you show it later. So that's supervised. So you've given it a set of examples that you've labeled in a certain way. So in some cases, you might not be able to do that. You might have data where you don't really understand the context of the data, different aspects of the data. And here you can use unsupervised learning. So then the algorithm itself tries to figure out what are the interesting patterns in the data, and how can the data be clustered into like islands. And then you could imagine maybe there are some variants of that. You can have the machine label the data itself and train, and then there's options where you can do small amount of that and then have the machine then classify the rest of the data automatically, and so on and so forth. So I tried to make one slide of a taxonomy of AI, but it was way too complicated, and so I'm going to kind of leave it at that, and hopefully point out how exactly the machine learning worked when I go through some examples. So as we talked about in the introduction, and made some jokes, AI as a field that's being invested in has really grown incredibly over the past 10 years or so. And these charts are from, you'll have to forgive me, they're from an organization at Stanford, but this is a very useful report that gets put out every year, the AI Index annual report. And the group there in this organization, they gather all kinds of statistics about investment, about how models are improving, and they document it all. So you can see that the amount of money, so the chart on the top here, top right, is in billions of dollars. The amount of investment has really been increasing tremendously, and I'm sure the 2024 number, when the report comes out in a couple of months, will be way up there, probably exceeding the 2021 number. In the lower chart, this is the investments broken down geographically. So you can see that in the US, that's the highest amount, or has had the highest amount of investment in AI. But there's significant investment also, obviously, in China and in Europe and the UK. So many people, I think of AI as like a general transformative technology, much like, say, the steam engine revolutionized industrial production, or electric power or IT became a part of our lives. And because I think it's been growing so quickly, and its boundaries and what it's finally able to do is also somewhat unclear, it's frequently framed as kind of a nation state competition, that whoever has the best AI technology will have an insurmountable advantage, say in economic production. And that remains to be seen, but it's where AI plateaus out, say, but that's a big concern. It's also often associated with a number of ethical dilemmas. AI is used for lots of things at the moment, with different amounts of oversight. Your credit rating, whether you get a mortgage, even in some states, what the sentence you'll get after being convicted of some crime. The judge can get an AI report on what the AI recommends you be sentenced to, and right, how do we know exactly how these AI engines are coming up with these recommendations? And then of course there's concerns about AI replacing people working, and how that will affect society and the economy. And as I mentioned previously, public and private investment has been rising dramatically. The number of papers that I see in the literature and the number of conferences involving AI been growing, and the attendance has been growing really rapidly. So a little bit more on the private sector landscape. Obviously, we're close to Silicon Valley, and many of the big AI labs, OpenAI, Google, Meta, are local, and they're pouring most of this money into developing better models. And we've seen substantial improvements from, say, ChatGPT 2 to 3 to 4. I think many people would agree they're quite a bit more capable models. And depending on what AI researcher you believe, some believe that what's commonly called AGI, or artificial general intelligence, is within sight, and some people think artificial superhuman intelligence is also on a roadmap. And I don't know if those people are right or not. We'll have to see. One of the things I would say, thinking about the private sector landscape, is that many of the models are focused on the results, like what does the model predict? That's the most important thing. And often in science, we want to know why the model thinks that prediction is correct as well. Often we'll have a set of theories and our own models about why something happens. And if the AI is just a black box that issues some prediction, we would like often to be able to map it to our understanding of why that physical phenomena might happen. And so we're seeing the fierce talent war between Google, Meta, Amazon, etc. It's very difficult to retain staff in the AI field at the lab, and many postdocs who get experience with it are lured away by NVIDIA and other companies. We've lost several people from NERSC to NVIDIA in the last couple of years, and it's certainly, in a sense, good for us. We like training people that go on to do other things. We would like to keep a kernel of staff with expertise here too. The chart here on the right shows kind of how AI has been spent according to sector, and there's a broken scale down here at the bottom. So the top bar is by far the biggest, and that reflects that most of the money is being spent on infrastructure and research. So as I'll describe in a minute, a lot of the latest models use huge computational resources to train and actually to run. And so a lot of data centers are being built out and populated with advanced hardware where these models are being deployed. Yeah, so the cost of training been going up. This is a great company that aggregates a lot of details about AI also. Epoch AI have another slide about some of the benchmarks they've developed later. But this just shows how the cost of developing models has been changing over time. And you can see back in the 2016, these were relatively inexpensive, just a couple of $1,000s to train. And if we look at GPT-4, which is one of the biggest recent models that's been trained, we're looking at about $60 million, something like that, that cost to train. And some of the more recent OpenAI models like O1 or O3, they cost even more. So this is a really substantial outlay, obviously, and these companies will have to show economic results to justify these huge investments. So let me pause there because I'm going to kind of dive into science and see if there's any questions at that point. Okay, I'm gonna press on. So not unlike the rest of the world, as it were, science has been adopting AI, and this is a chart that I grabbed from a publication that came out of Argonne a year or so ago, and it shows how different kinds of science have been using AI in publications. So whether they reference using it or not. And you can see that pretty much everything from agricultural and food science to psychology to physics to chemistry, there's this huge uptick in people using AI around 2020. Huge, either hundreds of % increase or thousands of % increase. So we know that it's very, very broadly used in science, and the question is, what are the different ways that it is being used? Let me see if I can answer. Well, let me say that our own lab, LBL, Berkeley Lab, we've been investing in AI for quite a while. There was a LDRD initiative back in, I think, about 2016, 2017, that kicked off some investment, and then slowly the DOE programs have been also offering funding opportunities to fund scientists to incorporate AI in their work. We've had a couple of summer schools to help people pick up the basics of using it as a technique. We have now a conference that happens every year in Monterey, which focuses on scientific data and using AI with data. And we've got a website to advertise many of the leading projects that are using AI. And you can see that it varies from transportation modeling to new materials to power grid modeling to cosmology, just pretty much everything you could think of. So as part of a workshop that actually predated workshop that generated the report that Lynn mentioned at the beginning of this talk, a few labs got together and we tried to create some kind of some buckets for describing how AI might be useful to the enterprise. And this is our choice. There's nothing standardized or I guess particularly remarkable about it. But and these categories are not even completely distinct. There's some cases where you might argue it's in two buckets at once. But let me try and describe at a high level, and then I have some examples what these might be. So starting in the top left, AI for advanced property inference and inverse design. So one of the things that you can do is you can for instance train a model to predict material properties. If you have a huge database of materials that you've either simulated by some other method or you've done experiments on, then you could train a model. And some of these models have pretty good utility at predicting the properties of a new compound. But then often these models are kind of like reversible. So you can reverse the model in a sense and ask it the question, so if I want a property X, what should the material look like? And that's something that's common in a lot of different AI models, which is not often possible directly with other ways of simulating materials. And we see that in models that might predict new materials for better batteries, either anodes or cathodes or electrolytes, protein design, better photovoltaics, things like that. Many people have built kind of bespoke models using the data that they've collected at the labs. Moving along the top, AI for robotics and autonomous discovery. So with the rise of having automated labs, so one of the cases of the ALS, you can load a sample into a beamline. A robot can do that remotely for you. Or in biology, you can have wet labs where you have a robot that does pipetting of one sample into another. So you could wire those robots, presumably, via an AI control system, and you could build into it some autonomous discovery techniques. So it could run a set of experiments, maybe overnight or over the weekend or whenever you don't feel like coming into the lab, and make simple decisions based on the feedback it gets from initial iterations of the experiments. And there are a few examples of that at the lab. Then kind of a slightly different one, carrying on across to the right here, is AI-based surrogates for high-performance computing. So while we have a lot of high-performance computing now, we have exascale machines, so very, very capable. Still, there are some kinds of simulations that take an awfully long time to run. And we want to run for longer periods of time, say in the case of weather prediction or climate prediction, and we want better accuracy. And those things just still consume an awful lot of time, even on an exascale machine. So is there a way that you can build a more economical AI-based model that will give, roughly the same answers? Maybe you sacrifice a little bit of accuracy, but runs a whole lot quicker. And then you can do many instantiations of your simulation, and I'll talk about that in a little bit. Then going along the bottom, AI for software engineering and programming. So I think maybe several of you may have tried things like Microsoft has a product Copilot, and it will, if you give it some high-level text directives, it will write code for you in a variety of different languages, and that's being used more and more. Probably not developing things from scratch, but certainly detecting bugs and writing patches, and maybe writing functions or routines to augment existing software. And it's quite remarkable. I've used this myself in the case where I have to write in a programming language that I'm not really familiar with. I don't know what to put at the header, but I know roughly what I want to do, and like make a loop that does this. And if you provide that information, these AIs will spit out the language with the appropriate syntax. And they'll also do these kinds of transformations for more complicated types of hardware. So if you've written a program that works well on your laptop, but you want to move it to run on graphical processing units, these models will make changes for you. Now, not completely perfect here, a lot of, I think, work to do, but a lot of really fascinating and useful results to come out of that. Then AI for prediction and control of complex systems. So we at the lab, we have plenty of complicated systems. We have accelerators, we have the ALS, we have genome sequencers. Maybe there's a way that we could build a model using AI where we can't build one from some set of master equations we have at the moment. So there'll be kind of a phenomenological model. We would take data about how one of these instruments perform, and we would build a model, so we would maybe be able to tune it up to run better in the future or avoid some kind of crisis. And one of the I was talking to Cameron Geddes at ATAP recently, and he was talking about one of the things that they really worry about is one of the big electromagnets they have. They're super cooled, so you can put the high current through them. Sometimes these magnets will quench, and the exact circumstances in which they'll quench is not easily modeled. But if you can train an AI based on previous examples of quenching to recognize when this might be about to happen, then it could save you downtime on the instrument. So lots of interest in building these AI-based models to control really complicated lab equipment. And then bottom right, probably kind of the most speculative in a way is, can you build a model that will generate a hypothesis for you? So maybe you feed it 10 most recent papers on a subject, some of your thoughts on it, and can the model design a set of experiments that you could then do that would either confirm or deny some hypothesis that would get you some steps down the road to wherever you're heading. And I think this is probably the most controversial. A lot of people have differing opinions about how much these models like ChatGPT know about the world. Some people think they know basically nothing, and they're just next word prediction engines. And some people think that they have developed some sense of the world, some kind of internal model, just by examining a lot of text. So this is very much an open question. So I'm going to just talk through a few examples at the lab of how this put into practice. And the first one is the ALS. So the ALS is a user facility, has multiple beam lines, a lot going on. The data that comes up off the ALS is getting more complicated. It's coming off much faster. Often you can get different kinds of data. And how do you deal with this deluge? And part of the answer, I think, is, well, faster analysis, so you can ask questions and get them answered, but also incorporating AI and ML into these workflows. And where there's this little schematic of a brain. These are points in the workflow of science where the ALS has inserted AI tools to help you make decisions, and I'll talk about that in the next slide. So these couple of slides are from Alex Hexmer, who works at the ALS, and Alex is doing these small angle X-ray scattering experiments, and sometimes right, the sample's not quite right, or the beam's not quite right, and he would like to know that, you know, sooner rather than later, and then he'd like to know what to adjust to make it better. And so they have this tool called GPCam, which is this kind of logo down here, and this is a machine learning model which actually works with very little data. So it slowly builds up an idea of the science problem point by point, result by result that you feed it. And not only does it give you a prediction of what the next result would be, but it tells you what controls to adjust to gain the most information to make accurate predictions in the future. So it's kind of a doubly useful. It suggests a way for you to explore how you might use the apparatus more successfully, and it gives you an idea of how to correct the result also. And this was a project that was a collaboration between Camera, which is a little math center within the computing sciences area, and the ALS. So by bringing applied mathematicians who know a lot about Gaussian processes and this kind of modeling with the experimentalists who have real real applied problems that they would like improvements on, has proved really useful. And so this is a little movie. I've always liked this, and so I included it today. And this is some work that Camera and the ALS did with GE Global Research. And what's going on here is that the GE wants to make turbine blades for either for jet engines or other turbines, and they want to make them lighter. And one of the ways to do that is to use composite materials like these ceramic matrix composites. And in this, you bond these fibers to some composite, and then you bake it to make sure everything holds together. And what we're interested here is that sometimes these fibers don't adhere, or the coating doesn't, the mass doesn't adhere well enough to the fibers. And ideally, you would want some automatic way of detecting this, so you wouldn't put a faulty turbine blade in an engine and have it, come apart. And so what happened here is that we're doing X-ray tomography at the ALS, and the results are being analyzed by a machine learning program that understands how to segment an image. So the red bulk object, what's happening is that the AI algorithm is segmenting. These are the silicon carbide fibers that you can see now, and then the green spaces, the green patches are where the fiber did not adhere to the composite. So what this does, it takes the human mainly out of the loop. So this system will produce a set of images and say these are the suspect areas in the turbine blade, for someone to follow up on. And so that's much more efficient than having someone having to go through mounds and mounds of these micrographs. So this was a proof of principle, and we continue to work with GE to see that whether that can be adopted or not. Okay, so I think many of you will have heard about this for AI for accurate protein structure prediction, and there were many many big headlines last year about AI changing everything in terms of structure prediction. And if we look at the top right here, there's a competition that is run every year called the Critical Assessment of Protein Structure Prediction, CASP. And what the competition was about was a protein, its structure was determined by X-ray crystallography, and then people were invited to predict just from the protein sequence what the folded protein actually looked like, and then that would be compared with the X-ray data, and people would get a score. And if you scored over 90, then pretty much you had predicted the protein structure completely correctly. So there were a bunch of proteins in the competition every year, and people tried different algorithms in order to be able to predict what their structure was. And you can see that over many years, 10 years, people were around the 40% with lots of different algorithms. And then in 2018, along came the AlphaFold AI algorithm, which was from DeepMind, which I think in 2018 was still an independent company, but was about to be bought by Google. And then DeepMind improved it even more to produce AlphaFold 2 in 2020, which got pretty near to score of 90 on the whole set of proteins. And last year, of course, two of the people from DeepMind, Demis Hassabis and John Jumper, won the Nobel Prize jointly with David Baker for his long-standing work on protein structure. So that was, I think, pretty unexpected that AI would do so well, but indeed it has. So, talking to Paul Adams, who's the ALD for BSA, he said this really was indeed a really long-awaited development. Accurate structure is now possible, but have to remember primarily because they have really great data. So years and years and years of the protein crystal data bank structures to work off. And this protein prediction, it's relatively fast. The inference engine just takes minutes to hours to compute the protein structure. And as well, there are uncertainties which are very, very useful. So where's this going in the future? So Paul Adams and colleagues are working on an open source version of this program that now expands, so not only proteins but looks at nucleic acid structures. That's a little bit trickier for a variety of reasons, but they hope to open source that when they finished training. But Paul wanted me to point out that although I think you may have seen headlines to saying that the protein folding problem is solved, it isn't really. The structure prediction problem may be largely solved, but how the protein folds is still really not fully understood. And it clearly folds not on its own, but with a variety of other biologically active molecules around it. And that process is still not completely understood. But nevertheless, models like this are really useful. So now I want to shift gears and talk about climate and weather prediction. So as I mentioned, we have the ability to run really huge simulations now with the latest high performance computing. So we can run weather and climate simulations for hundreds of years. But these are very, very expensive simulations to run. So what Bill Collins and his team and others, including staff at NVIDIA, have been doing is, can you build a climate prediction model which is data driven. So in other words, if we get a lot of samples of climate and weather from an existing simulation, can we train a model to simulate this much more quickly than the original full numerical simulation took? And the answer is yes. And here's a family of different data-driven weather prediction models that have been produced over the years, from initial work in 2018 to this biggest model called ForecastNet in 2022. And if we look at this progression, we can see that the resolution of the models is increasing dramatically from about a 6-degree resolution down here in the bottom left, down to a 1/4 degree resolution with a million pixels for the whole Earth here on this latest model. And so some of the interesting things that you can do with these models that sometimes run as fast as 10,000 times as fast as the original simulation is that you can run a lot of different ensembles, and I'll explain why that is important here. So an LLHI is a low chance of happening but high impact event. So it could be like a heat wave, or it could be a huge flood, and we want to be able to predict these events much better than we can currently. And the key to predicting these low likelihood events is to run many realizations of the climate or the weather for the same period of time, and start it with slightly different boundary conditions. And the only way to produce a large number of realizations is via simulation, but the original numerical simulations were way too expensive. So what Bill and his team have been able to do is to use these surrogate models, these AI-based models, to make the cost of these simulations cheap enough that they're able to run 10,000, 100,000 or million realizations and get the statistics and see these low likelihood events actually happening. And Bill's been doing some great work on this and producing some good papers. And at the beginning of the talk, I mentioned that NERSC was losing staff occasionally to NVIDIA, but this is one of the happy coincidences that some of the staff that we lost to NVIDIA actually worked on this this weather model with Bill Collins after they moved to NVIDIA. So it's one of the things that did work out well. This is another example which is a little bit different, but I thought was really very interesting, is ways to identify undocumented orphaned oil wells. And you may think, what's that? Well, over the many years that oil exploration has been carried out in the US, the many wells were sunk, and many of those wells are now abandoned. They don't have an owner, and it even become unclear where actually many of them were. And there's a case in Southern California where there's kind of a cul-de-sac, and there's methane emissions, and it was forming an uncapped abandoned well that no one knew was there. And so what some scientists led by Charu Varaharajan did was they tried to use, and have successfully used, AI to piece together information from various places. So there are actually USGS historical maps dating back to the 1870s, 1880s, and forward, where oil wells were carefully documented, and those maps. They exist in paper form. Some of them are faded and distressed, or maybe annotated, and very difficult for people to use those maps effectively. And so what the team did was they used an off-the-shelf image recognition network called UNet, and they fine-tuned it to be able to recognize these little black circles here that were the indicator on the USGS maps of an oil well, and fed all those maps through this AI pipeline to identify potential abandoned wells. And this project focused on 2 counties in California, and Oklahoma County and the Osage Nation in Oklahoma. And they were able to find quite a few wells here that had been abandoned and had no current owner, and transfer that information to the states to go out and do some more identification and remediation on them. So that's just kind of one example of taking the human out of the loop of a pretty difficult, painstaking task, and having the AI do the work. Right. So I've talked about all these examples, and I want to just speed through a few of these slides and leave you kind of with a final thought, which is so all this is wonderful, and my colleagues are doing great things with AI, but kind of a gap is that a lot of this AI funding within the lab has not been coordinated. Individual programs have given the go-ahead to explore the use of AI in such and such a thing, and many of the I think the cases of getting synergies between the project, maybe as projects have not been as high as they could have been. And DOE is really, it has a lot of data, it has HPC, has a lot of different facilities, and can do analysis. And we could really contribute to US AI leadership here if there was an initiative, I think, that was more focused. And I'm a little short on time, so I'm going to skip. We've been doing some workshops and reports to make the case for an initiative, and you can imagine maybe the initiative might be made of 4 pillars like this, and I'll just talk about them briefly and then stop for questions. So one of the things that you obviously need for AI is you need data, and not only do you need it, but you need to understand the quality of the data. You need to be able to transform it so it's ready to be ingested by an AI algorithm. And in some cases, I think that's well understood, like ingesting text is now, I think, very well understood. But what about different kinds of visual data or spectra or 3D chemical structures? That's, I think, much less well understood. And we need to be able to share that data very transparently with partners and make it easy to find and to use. And then for compute, I said that a lot of these models use a huge amount of energy. The Department of Energy, I think, has a stake in designing models that take less energy to train, and producing hardware which takes less energy to both train the models and to use them. And then, while there's been absolutely incredible progress in the private sector with developing new and bigger models, I think DOE Complex definitely has expertise in developing niche models for particular kinds of data, for maybe making these models more transparent in how they make decisions, and are more trustworthy. And then, if we have these three pillars going on, there'll be lots of applications of these models downstream to enable the labs to deliver better on its scientific mission, from new materials, new batteries, better code base, many other things. So I'm going to stop there and answer any questions you might have.